Okay, we're going to start looking at some examples from section 4.2 on what the derivative tells us. So if we were to look at number 12, number 12 in here, it says f prime of -1 is undefined. It tells us that f prime of x is greater than 0. Once again, on our intervals from -infinity to -1, and then f prime of x is less than 0 on our interval from -1 to infinity. So it's asking us, given these conditions that we have, we want to graph our function. So we want to give a possible graph for what's going on. So once again, if the derivative is undefined at a given point, that means when we come here to our xy graph, at -1, we know we're going to have something that is not differentiable right here. So once again, if it's not differentiable, we have either our slope is approaching infinity, or we have a cusp or a corner of something that is going on. So once again, this is kind of a breaking point that's in here. So this dotted line really isn't here, but I'm just using it so we can kind of see what's going on overall. As we consider this, we start looking at when we're less than -1. So over here in this interval, we talk about our first derivative is greater than 0. So that means whatever happening over here, we're seeing that we have a positive slope. Okay. Once again, then when we go to the other side, we're seeing over here we have a negative slope. Once again, coming to this point right here. And on this one, I'll just put a little kind of cusp, an inverse cusp right here. That way we know that we don't have a derivative, because once again, the derivative, the slope is going positive, is getting greater and greater. All of a sudden, then it starts negatively. So once again, we don't have this. So this would be a possible graph of what's going on. Other cases, if we look at number 16, number 16, what they do here is they give us our xy plane, and then they give us some values in here as we're looking at it. So just quick kind of drawing this out. We see that they give us this main graph that starts right here. We have a couple zeros on this, and we see that it's this curvature kind of going like this. Okay. So as we see this curvature, they tell us that this is the graph for y equals f prime of x. Okay, so that means that what we're dealing with here is we're dealing with the fact that we have positive slope, positive slope going to a slope of 0, and then we got a negative slope in this section, and then we have a slope of 0, and then we have positive slope in here. So when we see these slopes of 0, we're talking about local maximum, local minimums that could be going on in here. And then when we see decreasing or a negative slope, that means we're going to be going down our original graph, and then here we're going to have a positive slope. So what I'm going to do is, when our slope is 0, I'm going to kind of relate right here, because once again, this would be a local maximum, because we think back to our first derivative test, we talk about having a positive slope going to a negative slope, talks about having a local maximum. So we have an increasing slope going to a 0 right here, in which then it starts coming as a negative slope. Okay, and then we would come right here, we would be coming down. We then would be seeing over here that we would have then this negative slope going on, in which then we would be changing to this positive slope. Okay, so this is one possible graph that could be of this. Once again, just looking at some of those key incidents on that first order derivative, that we have positive slope, negative slope, positive slope, and then when our slope is 0. So once again, this would be the graph of our original function that would be going into it. So continuing on with some other examples. Let's turn this over here. So if we were to consider, myself lined up here again, number 20 then. Okay, on number 20, here they talk about that f of x equals x cubed plus 4x. It asks us to find the intervals on which f is increasing and decreasing. Superimpose the graphs of f and f prime to view your work. So we won't be doing the whole graphing part, but we'll be working through this algebraically as we're looking at this. So what we want to do is we want to find our first order derivative. So if we take our first derivative of x cubed plus 4x, we see that we have 3x squared plus 4. What we would do now is we would take a look at this and we'd say, well, when is this derivative going to equal 0? Because once again, when it equals 0, that's when we start talking about some possible change in our slope. And it gives us some different points to be working with. Once again, generally that local maximum, that local minimum that could be part of this. So if we were to set this 3x squared plus 4 equal to 0, we would see that 3x squared equals negative 4, x squared equals negative 4/3, x equals plus or square root of negative 4/3. Ooh, we're in our complex number system. So we see that whatever going on this graph, it is always greater than or equal to 0. Because once again, whatever number we put in here for x, we see that it's going to be turning positive, and then we're going to multiply by 3 and then add 4. So it doesn't matter if it's negative or positive. We see that the slope of this graph is always going to be positive. So because the slope is always positive, we basically talk about that our interval from negative to infinity is always increasing. Okay, so we have our increasing intervals from negative infinity to infinity. If we look at number 30 then, number 30 here talks about that, well, if f of x equals x squared times the square root of 9 minus x squared, and then they talk about the interval from negative 3 to 3. So here it's asking us to work with this as where is our interval of increasing, decreasing. So in order to find our intervals of increasing and decreasing, we're going to find our critical values that are within here. So if we take this first order derivative, so we take our f prime of x, we notice that we got a product of two functions. So we've got to apply our product to us. We're going to take 1 d2, so the derivative of the second. But remember, the derivative of the second is a function within a square root function, so we've got to apply the chain rule here. So applying the chain rule, we're going to take the derivative of our overall function, the square root of something, which would be 1/2 times whatever is inside, then to 1 less power, so the negative 1/2 power, times then the derivative of what's inside. So the derivative of 9 minus 2x is a negative 2x. Plus then the derivative of the second, so the square root of 9 minus x squared, d1, so the derivative of the first one, so the derivative of x squared then is 2x. So we see here's our derivative. Now let's clean this up a little bit. We see that this is a negative x cubed over the square root of 9 minus x squared, plus then we have 2x times the square root of 9 minus x squared, in which then we get negative x cubed plus 2x times 9 minus x squared, and then this is all over then the square root of 9 minus x squared. So this would be 18x and then minus 2x cubed So we see that we have a negative 3x cubed plus 18x over the square root of 9 minus x squared. So what we look at now is we want to know, when is this function going to equal 0? So when does f of x equal 0? Well, f of x is going to equal 0 when this numerator equals 0. So we take a look at having that negative 3x cubed plus 18x equals 0. We can look at some factoring properties on here. I can take out a negative 3x, which leaves me with x squared plus plus 6 equals 0, in which then we see that x equals 0 and then plus or minus the square root of 6. Once again, with that negative 3x equaling 0 divided by negative 3x would equal 0. Subtract, I'm sorry, I factored a negative out here. There should be a minus 6 in here. Let me correct that. I had it in my notes, but wrote it wrong. It happens. So this would have been x squared minus 6. So we would add that 6 over, take the square root. That's where we get the plus or minus the square root of 6. So we see that we have 3 points at which we have some change going on. So what we do now is we start looking at this problem given these 3 points. So what's ever going on with this problem, once again, it's only defined from negative 3 to 3. We see that when we have that negative root 6, which is approximately 2.5 roughly, we can talk about that negative root 6, and then root 6 would be right over here, and then we would have our 0 right here. We're seeing that these are where we should be seeing some changes in the function from increasing to decreasing going on in here. So what's ever going on, these are kind of like signs in here that are telling us that, hey, our slope is possibly changing in here. So what we do is we start picking values. So we look at a value in between here. So we would look at f prime of, let's see, if this was about negative 2.5, we can go like a negative 2.9. And then we would look at like a negative 1. And then we can do a value of 1. And then a value of 2.9. So what we would do is we would take our derivative function, which once again is this overall function right here, and we would plug these values in once again as it would look. So if we grab our calculators here, let's see if I can get you to see the calculator in here. We would look at having a fraction where we would have this negative 3 times, we can use just our negative 2.9, so go negative 2.9. Once again, this is going to be cubed, and then plus 18 times our negative 2.9. And then this is going to be over the square root of 9 minus, once again, our negative 2.9 squared. So when we type this in, we see that we get 5.025. So it's going to go equals 5.025 right here. And then just kind of quick bringing my calculator back in here, I'm going to go back and just change in my values here to be positive. So if I change these negative 2.9s to be positive 2.9s, we see once again that we get negative 27.297 then. And then we would just kind of come back in and we would do the same thing for our 1. So we change that 1 or I'm sorry, we change that 2.9 to be 1, and then we would put in our negative 1. If we put 1 in, we get 5.303, and then if we were to change that to be a negative 1, we would get a negative 4.743. Okay, so now that we start looking at this, we see that on these intervals in here, this first interval right over here, we're positive, then we're negative, then we switch to positive, then we switch to negative. Okay, so what we would come back then is we would say, well, on these intervals, so our increasing intervals are on our values from -3 to -6, and then we have also 0, the interval to a positive √6. Our decreasing intervals, so once again when we're decreasing, would be that -√6 to 0, and then √6 to 3. Once again, we are excluding the values that we found when we solved that plus or minus √6 and 0 in here, because at this given point, that's when the derivative actually equals 0. Okay? So one of the things that we would be noticing in here is we would also be noticing that at negative √6, okay, so this is an extension of the problem, basically using the first derivative test. So our first derivative test, once again we would talk about finding our critical values. So we have -6, 0, and √6 are our critical values. What we would see is that when we're to the left of negative √6, we see that we have a positive slope going to a negative slope. So once again, at negative √6, we would see, so when x equals negative √6, we would see a local maximum right here, because we have a slope increasing and then it starts decreasing once again. If we come back here, we have an increasing slope and then decreasing slope. Okay? And then once again, we kind of come here, back to increasing, back to decreasing. So we see that we have a maximum here. Once again, just looking at the graphs and looking at this first derivative test on here. Once again, we get the sign change from a positive to a negative. Also, we would have that local maximum, once again, positive to negative, so positive to negative at √6 is also a local maximum. And then when x equals 0, we would have a local minimum, once again, because at that local minimum we have our negative slope, then thus changing to a positive slope. So this kind of sums up what our first derivative test, and our first derivative kind of starts telling us about these graphs, and as we start looking at the values within, different features that we'd be working with on them.